Hi, in this video I'm going to talk about linking between MATLAB Simulink and FlighGear Flight Simulator. First of all, this video is just a demonstration for the output of this linking process, in which an already designed controller using the Simulink drives this airplane that you see in front of you in this simulator. And in the videos to come, I'm going to describe how to make this link in much more details. Okay, so let's press run. You can see here in front of you that the aircraft is flying in almost level steady flight. This Simulink model that you see in front of you has two controllers that run simultaneously. The first one aims at controlling the aircraft speed at above 300 knots. And the other controller right here is the one responsible for controlling the pitch angle of the aircraft, meaning whether it's looking upwards or downwards. Here I require from the controller that controls speed that it keeps about 300 knots, as I said. And then I require also from this controller that controls this pitch angle to have a pitch angle of 5 degrees. Okay. As a demonstration, we can see the states of this aircraft while being in action. Let's see the altitude, for example. We can see that it changes, actually it increases with time, and this is logic because this aircraft points upwards. It has a positive pitch angle. Also we can see other states like the aircraft speed. Actually it's increasing. You remember that we ordered this controller that we wanted the aircraft speed to be about 300 knots, and here we got about 289 knots, which means that we have about 10 or 11 knots steady state error, which is acceptable regarding that this controller that you see in front of you is just a controller that is made by sense, not based on any numbers or calculations, just for playing around, no more no less. Okay, so it's relatively good. I think that if we made this controller with a better design technique and with accurate numbers, definitely it will give a better performance. Let's see other states like the angle, the pitch angle that we have. We see that it's about 3.8 degrees, which means that we have a 1.2 degrees steady state error, which is relatively big. But let's change this angle. For example, let's make it about 15 degrees, for example. And you can notice the step that happened here in the pitch angle and this simple lag performance that you have just seen. And also we can notice that it keeps about 14 degrees with 1 degree steady state error, which is acceptable, regarding also that this controller was designed using sense only, not any accurate numbers or calculations. Let's change it back to 0, for example. You can see that this angle drops down in a simple lag manner, and it keeps almost 0 angle. Also we can see the throttle, the state of the throttle. For example, Oh, I'm sorry, just not here. You can find the throttle right here. Yes. You can see that's increasing a little bit. Maybe you can see that it's just oscillating, but if we make this airplane head upwards, I think this throttle will increase. Let's try. Okay, let's get this Simulink model. Let's tell it we want to have a greater angle. Let's say 15 degrees. Let's see them at the same time. Sorry for this delay. Okay, it's just changing its attitude, and then we see the throttle, it's increasing, and this is logic because right now the aircraft has a component of its weight trying to resist its motion, trying to make it slower, and then the throttle has to be increased so the aircraft can maintain the 300 knots that we ordered. Okay, you can notice that it oscillates. And if we decrease this angle, we can notice that the throttle should decrease. Let's try. Let's make it 0, for example. You can see that this throttle decreases because the component of the weight that used to resist the aircraft's motion upwards is no longer existing. So the throttle actually decreases. We can change it a little bit. We can make it -10. It looks downwards, and we can notice the notable change in throttle. Actually, from being almost close to 1 to about 0.6 or even less, 0.3 or something like that. Eventually, it will reach 0. Yes, this means that the aircraft speed is already faster than the 300 knots because the weight component that used to resist the aircraft motion is now in favor of the aircraft's motion, and it makes it faster. We can see the speed, for example, to make this more clear. Yes, we have a speed which is more than 300 knots that we need. Actually, 305 knots, pretty fast. Okay, I'll end the simulation right here. We can see from what has happened right now that I have designed a controller even with sense, with no accurate number or calculations, and I tested this controller on this simulator. Okay, and you've seen that I've been playing around with the numbers, changing the states, changing the inputs, and monitoring the states. Actually, I, for example, say if I make this input, I expect this output to be like this or like that. So we are aiming at the end of the day at putting this power of the MATLAB, which enables you to design good controllers, having many capabilities and powers regarding, for example, noise, different toolboxes, aerospace block, for example, whatever, and then simulating this, actually visualizing this output using something like this FlighGear flight simulator. Okay, this will give the hands-on experience on designing controllers and autopilots for aircrafts. Okay, this makes it better to visualize the effect of different inputs and different controller aspects on the aircraft motion and performance. And for this reason, I've been working on linking this flight simulator with the Simulink, so that we can create a universal tool that can be used for teaching control engineering in a good manner and autopilot design in a hands-on manner. In the next videos, I'm going to describe how to make this link in a more detail, and we can change even the aircraft model and the flight dynamic aerodynamic properties of the aircraft, and so on and so forth. Thank you for watching this video.